Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by a SETI PI who joined SETI in 1985, Laurance Doyle. And ever since he joined SETI, as I understand it, he's been interested in the search for circumbinary planets, which today he's going to talk to you about another stage in that search and the discovery. Laurance did his undergraduate work at the State University in San Diego, and then he did a PhD at the University of Heidelberg in West Germany, when it was West Germany. His PhD topic was looking at spokes in the rings of Saturn, which have now, in the time of Cassini, has been found to disappear, so that's a continuing quandary as well. Laurance also has been working on interpretation of dolphin language and on the astrobiological implications of communications between species such as dolphins and ourselves. Today he's going to talk to us though about his work on the Kepler team and that successful finding of the planet Tatooine, which was announced in Science just a few days ago. So if you'll join me in welcoming Laurance.
Thanks very much. When we realized we had a circumbinary planet, I wrote a kind of a funny email to the rest of the eclipsing binary working group, which basically our job for Kepler was to find eclipsing binaries. So we had to find our targets first, then we could go look for planets. So it took us 2 years after launch to classify all the eclipsing binaries. And I wrote, hey, we should ask George Lucas if we can nickname it Tatooine, ha-ha. But it turned out to be a major public relations thing, and we invited, as some of you saw at the press conference, we invited a representative, the director of Industrial Light and Magic. And he came and told us all about graphics and stuff and had a good time and hobnobbed with the scientists, so it all worked out really well. So tonight I'm going to discuss the detection of circumbinary planets, and in particular the detection, how we detected the first transiting circumbinary planet in the Kepler data, and why this is a little bit tricky, but once you find it, you really nail it. In other words, it's harder to find to begin with, but once you find it, you can determine its parameters very well because everything's moving. So you get to check on its orbit all along the way. So we think this may be the best measured extrasolar planet. In other words, the best measured planet outside the solar system. Now, some work went before. I was a co-author on this paper, the Dig et al. Paper, right here. And basically, the way we start out to try and detect extrasolar planets around double stars is to time the eclipses of the stars. And what we can do is we can actually say observed and calculated. So in other words, you see two stars going around each other and you calculate when they eclipse each other. And you can say if there's a third body out here, it's going to be offsetting the two. So in other words, the eclipses will happen a little sooner on time, a little later on time, a little sooner, and so on. So basically, if you have another object going around the eclipsing double star, it will arrive sooner, later, as the double stars offset around what's called the barycenter. So basically what this is a measure from zero of this star's eclipses drifting away from being constant. So we implied an 18.5-year planet, about 1.5 Jupiter masses. Some folks came along the next year and they did the same thing with HW Virginis, and they implied 2 planets. And then the following year, around an NN Sur, which is a white dwarf system, these guys basically thought they have a detection as well. So in other words, circumbinary planets were suspected, but about half the theorists didn't believe them and half did. In other words, they really wanted to know for sure if circumbinary planets could form in a solar system. And the idea was that a protoplanetary disk would form, but the binary star would dissipate the disk so planets wouldn't form. That's half the people. The other half said that the two stars would cause a density wave to propagate through the protoplanetary disk, and you'd actually get planet formation sooner. Well, here's basically what we look at when this is actual Kepler light curve, and what we see is the two stars going around each other, and as they go around each other, when the brighter star is eclipsed, the light drops. This is a plot of brightness on the vertical and time on the horizontal. This is called a light curve. The light curve, basically, this is called a primary eclipse, and this is when the brighter star is blocked by the fainter star. Then the fainter star gets blocked, then the brighter star, fainter. Now what we can tell from this is the two stars are about the same size. If one of the stars was bigger than the other, we'd get a square bottom. We also know, though, the two stars are not the same brightness. We know from the depth of this one that this one, a lot more light is blocked when this one is blocked than when this one is blocked. We also know there isn't a lot of star spot activity on this star, or we would have seen as the stars rotate this kind of wavy nature. So we can tell a lot from a light curve about the stars. Virtually everything we know, with a few exceptions of giant stars, virtually everything we know about the size of sun-like stars comes from eclipsing binary systems. And also, I might add, virtually everything we know about the size of planets comes from their transits, planets outside the solar system. So Kepler 16 is very well measured because it has eclipses and transits. Now this was the actual light curve of Kepler 16. And we can see that here are the primary eclipses in blue, and here are the secondary eclipses in yellow. So far as a normal eclipsing binary till we spotted an extra feature there. Now here's this extra green feature, and there it is again, and there it is again. And we're going, well, that's weird enough, but is it a triple star system, or is it another eclipsing binary in the background? So how can we tell? Well, one thing an eclipsing binary in the background wouldn't do is go around this way, stop, and suddenly reverse. Okay? But look what happened here. Here's a big dip, and here's a little dip. This is a quaternary event. So a tertiary eclipse, quaternary. Now the quaternary precedes the tertiary event. They've switched places in their time of occurrence. Eclipsing binaries don't do primary eclipse, secondary eclipse, primary again. They just don't do it. And here it switches back again, right here. So we knew for sure that this was an actual circumbinary object. But from the depth here, we knew the size of the stars and all. I'll get to that in a minute. But we still couldn't tell if it was a grazing star. In other words, the dip is shallow because it's just grazing the two of them, or whether it's shallow because it's a little object. So this shows a blow-up of those regions. This is the primary eclipse, followed by the tertiary event, followed by the secondary eclipse. Then we had the secondary eclipse, the tertiary event, and the primary eclipse. So this showed that basically they were switching places. So the first thing we did is we got our colleague Steve Howell to go to Kitt Peak and get a spectra. And we also got spectra from Harvard and later from the Keck in Hawaii. And the first thing we did is fit a model. This is basically the color of the star, and this is how much lines are being absorbed at that color. So what this is a spectrum. And basically from this spectrum you can match the red to the blue and say this is a star that's that temperature and it has this much gravity and so on. So in other words, you're matching the spectral lines to get the spectral type of the star. From this we knew that this star was a K2 star. That's more orange than the sun, and it's also smaller. It's about 69% the mass of the sun. So what you can do is you can plot its motion as it's being offset by the second star. From the size of this star, we can imply the size of the second star, and that is only 20% the size of the sun. And we'll discuss that a little more later. So you have an orange star and a red star going around each other, and you have them being displaced toward you and away from you. Now that's called a Doppler shift. And basically what we can measure is the spectra says if something's coming toward you, it's bluer, slightly bluer, and if it's going away from you, it's slightly redder. So what we can do is we can plot red up here and blue there, and we could see the primary star going red, blue, red, blue, red, blue. This is the model for the second star, but we didn't get spectra of it. Okay? So now we know we have a star small enough so that the dips we determined, those extra dips, could still be a planet. But we still didn't know for sure. We just said we can't rule out a planet. So what's our next line of defense? Our next inquiry is the fact that these switched. The dips, the extra dips are 1.7%, and that could still be a Saturn to Jupiter sized body if it's going across the middle of the star. And this shows the actual data when we plotted the first and last dip, and it showed that the middle dip was offset in time from the other ones. And you can't get that unless you're dipping across two stars that are moving. So in other words, what we have here is not a transit, in a sense, where the planet goes across the star, and then it does it again, and you have the period, and then it does it a third time. What we have here is the two stars silhouetting the planet as it goes across your line of sight. So it's drifting across, but the two stars are rotating behind it. So it's more like a silhouette than a transit. This shows basically the light curve. We've taken out the eclipses of the stars, and all you'll see is the transits. Now notice that one's not as deep as this one because it went across this star and then that star. So only look at the top line. The top line will shift to the second line, and this next transit will display on the top line. So we can compare them. Now that's interesting. This one's deeper. This one's shallower. This one looks wider now. So in other words, it went across this star, then that star, and the next time it went across that star, then this one. Now what happens if it hits the star just during an eclipse? Well, you can see that it didn't even transit this star. It stuck with this star all the way, and it made one really long transit. So when you look at eclipsing binary transits, you get these quasi-periodic signals. They're predictable, but they're not periodic. So you can't just use a Fourier transform to overlap the transits. So in other words, automating this is not really possible yet. People are trying. But it's so odd. You can predict, but you have to do like a billion models and compare them. And what it is, for those of you that are interested, is called a matching filter. That's what we use. But for Kepler 16, I used what's called an eyeball. So what's the next thing we want to do? Well, the next thing we want to do is ask ourselves, if there's a star there that's going around both these guys, it should provide a pretty good tug. So remember that O-C diagram we saw for CM Draconis and HW Virginis and all? This is the expected, which is calculated, and this is the observed. And we watched, and it varied up and down by less than a minute. Notice that that's less than a minute. So in other words, we knew that a star would have made the times of eclipse vary by 40 minutes if it was a brown dwarf, and vary by 200 minutes if it was a star. So seeing this was so small, this said to us, uh-oh, we probably for sure have a circumbinary planet. So anything more massive would have caused these little stars to vary by much more, by probably 50 times what you see here. So in other words, by the tug on the planet's tug on the stars should have made the stars change their rotation period. Now this is, don't run, this is for those of you that like this sort of thing. There'll be a quiz in the morning. Okay, well there's two ways you can detect planets by timing. One of the ways is that you can have a planet really far away, and think of it as a teeter-totter, a seesaw with a fulcrum. The fulcrum has to be closer to the fat guy than the skinny guy. Skinny guy is the planet, fat guy is the stars, the two stars. Now, what happens if you spin it, you spin the fulcrum like this, the big guy is going to be displaced toward and away the fulcrum, right? So he's going to be displaced toward you and away from you as a balance for the planet. Well, there's light travel time across that displacement. So here's the eclipsing binary, and here's the planet going around every decade or so. And there's sufficient offset because the planet's so far away to actually time the difference. Is everybody with me? You're timing the eclipses to see how much they've been offset. And if they're offset periodically, something is going around the system. Well, that's what this equation says. This is what you need to do. However, Kepler 16b was so close that the time travel across the offset was not very large. It was less than a few seconds. So, but what one of the colleagues, Dan Fabricki, he said, well, wait a second, it's close enough to tug on the eclipsing binary itself. Well, that would be this equation down here. And what that means is instead of the period of the eclipsing binary remaining constant, remaining unaffected, and being offset, actually it's when you put it close, the period changes. And that's because every time the eclipsing binary goes around, the planet tugs on it. So the period is changing. The eclipsing binary, Kepler 16ab, is actually changing its period. And we could compute the tug, the strength of that tug. And the strength of that tug is shown here. Basically, the tug was, this is the tug on the primary eclipses, and this is the tug on the secondary eclipses. And basically, this is our model. Those triangles, those diamonds, are our best model fit. So we could fit a model exactly to the strength of those tugs. That together with the size of the planet measured from the transits, we could get the radius and the mass of the planet. And all of you have probably seen, not this one, you've probably seen the movie. This is Kepler 16b then. It's about the mass of Saturn. It's in an orbit that matches Venus's almost exactly for eccentricity. It's in a more circular orbit than the Earth. It's also lined up with the orbital plane of the two eclipsing stars better than the planets are lined up in our solar system. As you just saw, not only do the stars eclipse, so we can get the size of the stars, but the planet transits both of them. And it's not exactly in the Milky Way, but we fudged a little there. Let's see. So basically we were able to get the mass from the variations around the eclipse times. Now you can't do that with single star transits. They don't eclipse and stuff. So in other words, while these are hard to find, once you find them you can really learn a lot. So here's the full light curve, and we extracted what a primary eclipse looks like. Note the scale's different. Note this is the largest feature by far. This is about 14% dip. Then we have this is the secondary eclipse, and that's about a 1.6% dip. And then we have the primary transit. That's when the planet goes across the bright star. And then this is the secondary transit when the planet goes across the faint star. And notice here where we pointed out that the green switches with the red in order. We now have 3 more of these. And I might add some other circumbinary transiting planet candidates. Now that we know how to play the game, it took, I don't know how many decades to find the first one, and then it's like spotting Waldo or whatever that guy with the striped shirt is. Once you know. And this is just to show you, each of the points is a data point from Kepler, and the line is the model. So any place you look, we nailed it. Here's the model right here. Every line goes through every point, and this is the whole light curve we analyzed. So, and Josh Carter was the main guy that did this at Harvard. Okay, so what do we have here? We have a planet, a star, that's about 69% the mass of the sun, and we know its mass to within 0.5%. When I started rattling off some of these numbers to colleagues who wanted to work with it, 0.6897, they're going, come on. 0.7, they're going, no. 0.6897 plus or minus 0.0035. By that time, they were laughing. And the radius, 0.6489 plus or minus 0.0013. Just going like, this is ridiculous. We just don't do this outside the solar system. So we know the radius to within 20%. Now that's going to be an interesting little star. I'll talk about that in a second. Everything about this, yeah, 0.2%. That's what I meant. Yeah, thanks. So 0.2%, just for the film. So yeah, this turns out to be pretty interesting because it's a main sequence star. That means it burns fuel normally like the sun does. But it's the smallest known directly measured main sequence star. So it's going to be of interest to stellar model people. This star is of interest. Sorry, this one. Oh, you know, I messed that up. Let's see. No, that's correct. This star, star A, is interesting because it rotates slowly like the sun every 35 days. But it also has intense star spot activity, which is supposed to be the result of twisting magnetic field lines. So people that study star spots are going to be really interested in star A. Star B, which is 20% the mass of the sun, we know very well. It's probably one of the best measured small main sequence stars, if not the best measured. And we also know the radii very well because the transits are constantly happening, as are the eclipses. And we also know the mass of the planet pretty well, better than 5%. And of course the radius to about 1/3%. So it's pretty good. So this is what we have. A circumbinary planet. This orbits every 229 days. So once again, it's close to the 224-day period orbit of Venus. The eccentricity is 0.0068, which is really close to the 0.0069 of Venus's orbit. So, but it's outside the habitable zone, and that's because these two stars are much fainter than the sun. The binary has a 41-day period. And the eccentricity of the binary is 0.16. So they go around each other in a rather eccentric motion. But the planet itself's eccentricity is very small. That's smaller than the Earth's, I believe. And we know things, for example, like the density of the planet. And we know the inclination of all the system, 90.34 versus 90.03. So in other words, the binary plane is lined up with the planet plane to within 1/3 of a degree. So that's very fortuitous because both those are now lined up with us so that we have them eclipsing. So it's kind of a gift of the universe for us. Yeah. We got a fairly easy one to start with because the two stars are not interacting either. Each of these stars is blown up by a factor of 20 from their actual size. Now, eclipsing binaries can get so close to each other that they're actually throwing mass back and forth. That would have confused us. We would have been out to lunch there for a while. We also got a nice circular orbit. So in other words, the solution to all this was pretty good. Now, Josh Wynn, one of our team members, actually got time on the Keck, and he measured what's called the Rossiter McLaughlin effect. And basically, remember the red shift of the spectra, blue shift, red shift, blue shift, blue shift, red shift, blue toward you, red away from you. Well, you can actually measure the rotation of a star by how much red shift and blue shift it is. If you rotate it quickly, then it'll be very red and very blue on either side. So you get a broad spectral line. What happens if you put another star in front of it eclipsing? Well, what you actually get is you're blocking out some of the blue light coming toward you. And then you let it all through, and then you block out some of the red light. And what happened to that radial velocity curve is this. You get it going up and then down. It blocks some of the blue, then it blocks some of the red, then comes back. And this was his measurement one night, and he took a second night just to make sure he wasn't imagining this. And sure enough, nothing happened there. So in other words, he actually got a measurement of the rotation of the primary star. Now what does that tell you? Well, that tells you the inclination of the star, how the rotation is inclined toward you or away from you. So we wanted to see, since the orbital plane is lined up, the binary is lined up with the planet, how about the star? How is it lined up? Is it rotating in the same plane? And the answer is yes. It is. It's rotating within precision. It's exactly pointing, here's the rotation axis of the binary, here's the rotation axis of the planet, and here's the rotation axis of the star. So the primary star's equator is also lined up in 3 dimensions, by the way. I think this is the first measurement outside the solar system in 3 dimensions of the rotation axis of a star. So in other words, it's lined up as well. So the modeling people, bless their hearts, have got to go out and get this thing delicately balanced, get the star exactly lined up with the binary plane, with the planetary orbital plane. So I wouldn't like to have to model all this. This also isn't exactly how the sunset would look. I'll go back to that in a second. Now this is actually a plot of the smallest known solar type stars. And it's a plot of their mass versus the radius. And we can see by blowing up this region here that this star, this is Kepler 16b, the smaller star, joins some other stars, but it's the smallest of the group. CM Draconis has 2 similar type stars, and notice that they are not able to be fit with the models. The models underestimate both their radius and their mass. And this is called Kepler 126, and it held the record. CM Drac held the record for the smallest directly measured eclipsing main sequence star for about 50 years, 40 years. Kepler 126 held it for about a year. Kepler 16, I don't know, we'll see how long it holds it. But the reason it's of interest is it's not only the smallest, it also is above the radius and mass that the models can fit. So they're basically saying, guys, you have to go back to the drawing board and get the models to go up to there, not there. But the other thing that's interesting is Kepler 16a is so much different a mass. It's way up here in mass and radius compared to the other one. So before, we only had similar pairs. Now we have this one way down here and this one way up here. So not only do the planetary formation people get to go to work, but the stellar model people get to go to work. Okay. We use the term direct, hopefully, at the press conference. It wasn't the first unambiguous, or we didn't want to imply the previous work hadn't been done. So we had to be real careful. And now some words that sound similar to English in English are not similar in science. So we carefully chose the term first direct detection because transits were considered too complicated. And we figured everybody that has direct deposit would understand the term direct. Although there was some debate about using direct. The orbit of the binary is lined up with the orbit of the planet to within 1/3 of a degree, and the rotation axis of the primary star is also lined up exactly. Probably the best measured radius of any planet outside the solar system. It's a very small star, which is going to be interesting to those guys. The whole system's about 200 light years away. And we've estimated it's 3 billion years old, but that's 3 billion plus or minus 2. And that's because rotation period is usually indicative of a star's age, but then so is star spot emission, and so we have both. So we don't really know. And finally, this provides really strict constraints on the formation of circumbinary planets. Well, let me show a movie just a second again. Okay, let's see if I can do this. Okay, here's what a sun, if you're just behind the planet, say in a synchronous satellite, here's what the planet would look like. From the planet, here's what the star would look like. Okay, that's the kind of sunset you'd see. Kind of a do-si-do sunset. So no sunset would be the same. Of course, the orange star would cast a shadow, but that would be filled in with a red star when the red star was displaced. The red star would cast a shadow, but that would be filled in with the orange star unless they were eclipsing each other. So it's really interesting to think about what it would be like to live on a circumbinary planet. Oh, okay. It's subtle. You can see the star spots going around. We just imagine those. I mean the atmosphere. Yeah. Josh Carter did this movie too. Now, is it a month, a day? What do you use for definitions of stuff? Sundial technology would have taken the invention of calculus first. Let's see. So I want to play one more movie for you. Hold on a second. Okay, now this is a movie that Josh Carter put together of all the modeling that we did. And this is the primary star, what we imagine it might look like, a K2 star. This is an M5 star, and we imagine it might look like that, putting out most of its heat in the infrared. This is what the planet might look like. We figured Saturn, but it's half gas and half rock and ice. So it may be more like Neptune, looking more like Neptune. And here's the actual planet and, you know, a bird's eye view. And this will show you our view of what's happening while this whole proceeds. And then what this will show you, this is time, so this is the light curve here, the relative brightness. It'll go primary, secondary eclipse. And this will tell you the speed at which the movie's running. So you don't have to wait too long in between. So this is the primary eclipse coming up right here and right there. And right here you'll see it. There's the small star going in front of the big star. And the planet's over here. So now we speed it up a bit. And here comes the primary transit. And that's, there it goes. There's the planet going across the big star, and that's about a 1.7% dip. And we speed it up again. And now here comes a secondary transit. Look carefully, there it is right there. So that was a little bitty. We had to look for that after we found the others. We predicted when the next two secondary transits would occur, and we found them. But we found them just where we were looking for them, so we kind of made a prediction. And here comes the secondary eclipse, so the bright star goes in front of the fainter star. Right there, and that's a 1.6% drop in brightness. And then we can speed it up again. The ratio of the periods is 5.5 to 1. So in other words, every time the eclipsing binary goes around itself, the planet orbits 5.5 times. Then we just speed up the whole thing and you can see the regular events. We're skipping the eclipses and slowing it down for the transits. I'll let you see one more transit then. We have twice the amount of data now that we had when we published the paper. Here comes the next transit, primary transit right there. Oop, happened quickly. No, sorry, that went behind. That was the planet going behind. So that was called an occultation. When something about the same size goes in front of something else, it's called an eclipse. A little thing goes in front of a big thing, it's a transit. A big thing goes in front of a little thing, it's called an occultation. So we'll do one more transit, I think. Now what's interesting is these transits are going to go away. Even though it's 1/3 of a degree, the planet's so far out that a slight rotation is going to move the nodes away, and we're going to miss transits. I'll let you have, I might as well, you get the idea. Oh, well, here comes a secondary transit. We'll let you do that. Little bitty dip right there, see it? Okay, we'll go ahead and see a primary transit too. Here it comes. Okay. Nice. Okay. So, let's see now. Let's go back to PowerPoint. Oops, sorry. Review. Now see, you can now see how these were scaled. You know, this is very much smaller than that, for example. Okay, what's next? The next thing we'd like to do is look for moons. Beside looking for the next transits, we've requested short cadence data, and what that means is instead of getting a point on the light curve every half hour, we're going to get a point every minute. So in other words, we get much higher resolution on all the transit features. We want to look for moons around the system. Is there anything of astrobiological interest? So a colleague of mine, Martin Heath, pointed out that due to the eccentricity of the two stars, when the bright star is closer at the long axis of the eccentricity, and that aligns up when it's an inferior conjunction with the planet, you're going to get the bright star closest to the planet. And that insolation, that is the amount of brightness that the planet's going to get, is going to be very close to what Mars gets. So in other words, we're very close to the outer part. We're just outside the outer part of the Hab zone. But notice when you have a habitable zone around the sun, that's defined as a certain distance, and it's a shell. You know, a certain distance around the sun that's basically a shell of a certain thickness. We know that Venus is inside that thickness because it's lost its ocean. That's called the moist runaway greenhouse effect. And Venus is basically telling us, see this? Don't do that. We don't want to do that. We don't have to do that. We already have an example in the solar system, and the Venusians blew it. As far as Mars goes, Mars is what you might call a runaway refrigerator. It's at a distance such that if you add greenhouse gas like CO2, it'll snow out. The snow makes it more reflective, which cools it faster, which makes it snow faster. You get a runaway refrigerator, or runaway icing. So, but what happens when you have a double star where the stars are changing their distance to you? You have a dynamic habitable zone. It's not a place in this solar system. It's this ongoing thing that moves with the two stars. So in other words, the habitable zone comes up and away and up and away like a tide. And that's pretty interesting. And that gave me the idea, which I'm working on the paper now, of tidal heating. As we know, Europa and Io, moons of Jupiter, the atmosphere, the rotation rate of Jupiter causes a bulge. The bulge yanks on the moon Io, for example, and Io says, okay, I'm coming, and the other moons go, no, you're not, come back here. So poor Io's being, you know, like bending a wire. It gets hot before it breaks. So Io and Europa are both very warm because of tidal heating. Well, tidal heating will be a non-negligible effect in this system, but the tides won't come from the squishing back and forth between moons and the atmosphere of a planet. It'll be caused by the changing distance of the two stars. So if we add tidal heating, we'll see. So this system might be of astrobiological interest. We'll see. And thirdly, we want to discover more circumbinary planets because we want to see how you have one example of anything you can't really tell. What's interesting about this system, it's another example of a planetary system, fundamentally different than anything we ever discovered. So I said basically, you won't be able to observe the transit of Kepler 16b until October 22nd, 2016. And that's in this hemisphere. But next year, on June 28th, right there, you will be able to observe the transit of Kepler 16b across the bright star. It'll drop 1.7%. People in China, Russia, Korea, Japan, India will be able to see it. So if you're an amateur and you want to see the transit of the first circumbinary planet since its discovery, the transiting circumbinary planet, I would go to one of those countries and set it up, and don't delay because the transits go away for 24 years in 2018. So another really cool thing about this system is it's got this Halley's Comet kind of aspect where I know folks will be talking about us in 24 years. And the secondary transits go away in 2014 for 45 years. So maybe I'll stick around for that. That would be pretty fun if we're not there already. But so the transits come and go, and that's kind of a cool feature too. So we called it Tatooine, not just for the PR, but also because it's the first planet discovered that will see two stars as a sunset. The disk size is comparable to the disk size of the sun. It does increase the probability of Kepler finding a habitable planet, because there's no reason you can't have a habitable planet in a circumbinary system that we know right now. And lastly, the sunsets must be amazing. I'll just add one more addendum. I won't go into detail, this is another talk, but there's a new way to detect, we invented a new way to detect circumbinary planets. I know, we haven't published the paper yet, but, and here's what happens. As it's basically the planet reflects the light from the two stars, but that is usually a kind of a modulated sine wave. As the planet, like the phases of the moon, it gets brighter and fainter and brighter and fainter. But it also looks like star spots and all sorts of stuff. But around a circumbinary planet, the planet sees the eclipses. So actually the eclipses are reflecting off the planet. And here's what's cool, is you can measure when the planet's here, the reflections happen one semi-major axis later. So you can get the period of the planet, but you can also get its semi-major axis. In other words, if the planet's here, you see the eclipse and you know when the planet should have seen the eclipse, and then sometime later you see the reflection of the planet off the eclipse off the planet's atmosphere. Does that make sense? Well, notice it's going to be delayed by how long it takes light to travel from here to here. So then it reflects to you, and you say, oh, I see, that's the light travel time. For Earth, it would be, if these are two suns, for Earth, this would be 8.5 minutes later, you'd see a reflection. And then you say, okay, well, what about the other stuff? Well, the other stuff is, if the planet's here, then it's twice, unless it's inclined, in which case it's the light travel time to the planet, and the time back to you will be the sign of the inclination. I won't worry about that, but for those of you that like these sort of things. So notice we don't need spectroscopy to get a planet this way. I'm looking at Kepler data now to see if we can use this new method, and we're simultaneously submitting this to the Astrophysical Journal as a new way to detect circumbinary planets. So I think that's everything.
Laurance, can I kick off the questions? So given that you now know Kepler 16 so precisely, can you put an upper limit on other planets in the system? Like, can you say whether planets of a certain mass are present?
Yeah. Actually, we can put a limit on whether they're planets inside, because they would be unstable, we think, unless they're very small mass. As far as planets on the outside, we can't do that as well as you might expect. And the reason is because the period of the planet's so long. It's 229 days. And to really see perturbations in the orbit, we need a few more. by the time the Kepler mission's over, we'll have a few more, and we might be able to say there's no Jupiter mass within half an AU kind of thing. But we can't do that yet because we only actually have a few orbits. Yeah.
Other questions?
Thanks for a great talk.
Thanks.
In one of the animations, the light from the primary star was visible on the secondary star, making it have phases. Was that increase in brightness of the secondary star actually visible in the data?
You mean a reflection?
Yeah.
No, because
It can be a pretty small effect.
yes, it's particularly small because the period's 41 days. We definitely see that effect on close binaries. What we see with the periods, binaries can have periods so close they're touching. But even if they get within a few days, then the brighter star will actually reflect off the surface and actually heat it.
Right.
So we actually know of a star system where the two stars are not eclipsing, but they get close to each other and they start reflecting light off each other. And we see the light curve actually do a reverse eclipse. We call them inverse eclipse systems. KOI-54 is one of them. And they also start to oscillate. So that reflection effect is important to model, and not to be confused with the sunspot cycle, which it's easy to do. Yeah, stars are acting a little bit like mirrors.
I guess I have two questions. First is the system is not chaotic, is that?
It's not chaotic. We ran it a few million years in the future, and we saw no sign of instability.
So,
although it is very near what was called the theoretical limit, the ratio of the semi-major axis is about 3.14 to 1. So that's pretty close.
you mean it could be?
I don't think it is going to be. In other words, this is an observation. The theory people, some of the folks said, well, that could be chaotic. It's like, no, we did it.
Wow.
We ran it.
Some ratios would be.
That's the point. Some
Oh,
ratios could
yes,
be
some
chaotic. I
ratios
see.
would be, yes. If you get closer than, well, now it's 3. It used to be something like 4 is what everybody used. But now, if you get much closer, if like the inner part of the Hab zone around the system, I'm not sure you'd have a stable planet for very long.
But so therefore, it's in equilibrium. It is a system
Yes.
in equilibrium.
Yeah, it's amazingly, exquisitely balanced, the
It's a
whole
clock,
system.
isn't it?
Yeah, yeah. Well, the eclipses are changing by a minute, you know, because of the, yeah. Oops. Next one.
You showed a plot where you were looking at the tugging of the planet on the two stars.
Mm-hmm.
And I noticed that some of the data points, you got good agreement within the error bars, but there were some where you didn't have agreement. The differences were outside the error bars. I wonder if that points to yet another planet in the system.
Yeah, that's a good question. There might be another planet in the system, but this is missing data. This is our model without data, and this is a model without data here. So with those, don't judge those 2 points because the spacecraft had to roll.
But there are two outside the error bars of the, in
Right,
the blue
yeah.
on the
Here's-
on the top. On the top.
Yeah, here's one outside the error bar there, and there's one outside the error bar there. And this one is, well, I guess it's touching. So yeah, maybe. We'll see how it goes. Once again, we need more cycles to be able to tell. But that's a very good question. We call them the TTV group. We're the EB working group, eclipsing binary. There's the transit timing variability group. And they would be, you know, that's one of the things they're going to jump on, I have no doubt.
If you had the next Kepler, like the next spaceship or telescope that went up, what would you want it to do better than what the current Kepler does to help you with these kinds of models and studies?
That's a good question. If there was to be a Kepler 2, I would want it to bring color filters. This one we didn't even bring a shutter because we don't want any moving parts. I want everything to work. The trick of Kepler was to get things to measure the brightness of stars 100 times better than anybody ever could. The next thing, though, I think would be to get color, to get basically color data. What I ideally want to do is also get the spectra of the stars as they transit each other. So you look at the entire spectrum, you have all these lines. Then some lines go away when the planet goes behind, for example, the star. So you're going, those lines belong to the planet. As it went behind the star, those lines disappeared. So you get the atmospheric constituents of the planet. And if some are oxygen, you get that 9.6 oxygen ozone absorption feature. Well, oxygen's so reactive, as we know, when a nail rusts, it takes oxygen out of the air. And we know that the oceans were rusted by the bacteria in the early days. So if you find free oxygen in the atmosphere, you've got evidence of photosynthesis, pretty much. So if you get that ozone feature, absorption feature, you've got a forest. So that'd be the next thing, detection of extraterrestrial forests. Forest in the broadest sense, it could be algae. But anything that photosynthesizes could be detected that way. So that's the next step. But once you find Earths, I think people would be interested in doing that. You know, okay, here's the Earth in the Hab zone. Let's see what it's got.
Can I just ask you a question first? Laurance, you showed a list of the eclipses from Earth. Now, Kepler's not in the same location as the Earth.
Right.
Can you step us through the advantages that Kepler has that mean that it doesn't have problems like Earth does?
Well, one thing is it doesn't have the atmospheric variability. So one of the big things about Kepler is it was able to show that all stars are variable stars. We didn't know that before. But so we couldn't have seen the quaternary events. In other words, the secondary eclipses we would not have picked up from the Earth. Nobody can detect those from the Earth. They're less than 0.1%. So you can see the primary eclipses. That's why they're the only ones I listed. 1.7% with a good amateur telescope and a 6 to 8 inch and a little CCD that you can buy from S-Big or something, you can detect a 1.7% drop.
How bright?
And by the way, it's 11.5 magnitude. So you can see it with binoculars. If you want to find it, you know, you look straight up right now, there's a summer triangle, right? Deneb, Vega, and Altair. I knew if I paused, it'd be, that's great. I used to go to the Telescope Makers Conference in May down in South California, and we had the amateurs versus the professionals. It was a workout, I'll tell you. So then you look, and beyond the Northern Cross with the 3 stars, there's Deneb and Albireo, and then the 3 stars across. Extend them, and you have the wingtips of Cygnus. On the easternmost, there's 1 bright star greater than 4th magnitude on the wingtip. On the westernmost, there are 3 stars. Okay, so far? The middle star of those 3 on the wingtip of Cygnus, farthest west, is called Iota II Cygni. Iota II Cygni is a magnitude 3.5. If you take binoculars, you'll be within 1.6 degrees of the field of Kepler-16. So you can actually, with binoculars, see Kepler-16. If you want to find her chart, when you get that far, it's on the NASA website, Kepler NASA website. They have these nice finder charts. You will find us looking down the galaxy, so it's a super crowded field. But if you like star hopping, it's for you.
I'm puzzled. Your comment about the habitable zone kind of coming and going, isn't it extraordinarily unlikely that forms of life would be able to survive that huge range of temperature features and so
it's
on?
a good question. We worry about a couple degrees warming, global warming and stuff on Earth. This is 30 degrees difference in the outside the atmosphere as the K-star moves toward and away from Kepler-16b. 30 degrees is a lot, but it only lasts a month. We go into the dark every 24 hours. We spend half the time in the dark, and we don't freeze out because the thermal inertia of the atmosphere is really good. As a matter of fact, you notice it gets colder after the sun starts rising again, higher in the sky. It isn't nippy cold December 21st compared to February, and that's the thermal inertia. So when you have a nice thermal inertia in your atmosphere like the Earth does, you can get by with a lot. Yeah, right. Yeah, and that's a good point that, you know, things can adapt. We have some extremophiles that live in the ocean vents and just all sorts of stuff. Psychrophiles, you know, that live in 3 degree, that's the largest habitable zone we have on Earth, is about a couple degrees above freezing, because most of the ocean's a couple degrees above freezing, and that's the largest hab zone we have. So this isn't typical, you know, but yeah, good, that's really good. We have to think of these things this has not been addressed for circumbinary planets. That's why it's so fun. We're in a whole new thing again.
Yeah, I was a little curious about, you talked about possibly looking for moons, and it seems like it would have to be a pretty large moon compared to the planet for you to have any chance of detecting it.
Yeah, good point, yeah. Say your telescope isn't big enough to detect a moon transiting. Like say you could detect, Kepler can barely detect an Earth. We need an extended mission for Kepler because it turns out most of the stars sparkle more than the sun. We had assumed on launch, and nobody knew because nobody could measure that well, that the stars were about as active as the sun. Turns out that they're more active, so we need an extended mission to, it's like you're going to say the Gettysburg Address to your friend and you dial them up and the phone's going, you're going, I can't do this in a minute, it's going to take 5 minutes because of the noise. That's what happened to Kepler. Okay, back to your other question. What was your question again? I'm sorry. Oh, yeah, the moons, yeah. Okay. Say you have the Earth and the Moon system, and you knew that the Earth goes across once a year, and you watch it for 3 years, and you see 3 dips, and you say this year-long period, but you notice something odd happened because you're watching the 3rd transit, and you're going, ready? It's going to transit now. And nothing happens. It's 2.5 minutes late. What happened is the moon led, just happened to be here, and instead of the Earth by itself going in front of the sun, it was going around the moon, and it just so happened when the moon was in front. Say this is the moon and this is the Earth. It just so happened the moon was in front when it led. It would delay by 158 seconds the transit of the Earth. So that's how we're going to find them, by their delay in the transits. And that could be some of those effects.
Okay, my question is, binary stars are fairly new to me, and I was going, is there any upper limit that has been established through observation of how many stars can be in close proximity to a point where they share a point of gravitational, what did you call that?
Berry center.
Yeah, the Berry center.
Yeah, we know that now because of Kepler. 1 in 70 star systems are eclipsing binaries. So the probability of finding 2 stars that are close enough to actually eclipse, we just took from looking at one part of the sky for a long time, and we now know that about 1 in 67 systems are eclipsing double stars. Half the stars are double already, but they're usually wide. They're wider apart.
More stars than that, though.
More
Are there ones with more stars than just 2
sure.
that have been observed?
Yeah, we've also found a handful, about 24 triples. Yeah. And we're looking for, I don't think I let the cat out of the bag, but we're presenting a paper at the American Astronomical Society where we think we have 5 stars. But we're not sure. The one that eclipses here may or may not be bound to it might be background. But sure, Castor, Castor and Pollux and Gemini, Castor's a 6-star system.
Wow.
Yeah, so thank goodness we didn't get that first. Just one at a time, please, But yeah, we do have 4 and maybe 5-star systems coming down the pike. Those will be published in the next year. And there's going to be some more circumbinary planets too, very soon.
Okay, well, if we have any more questions, I encourage you to come up and speak to Laurance. Laurance, we have a special SETI mug. I'm sure you haven't got one of those on your shelf.
No, cool.
So
thanks.
Please join me in thanking Laurance for his great talk.
Thanks.